Welcome back. And now we're going to talk about ratios and proportions. Tonight we're going to talk about two different sections. We're going to cover section 7.1 and 7.2. It's a 2-for-1 night. So we're going to go ahead and get started with the ratios. A ratio. Well, we've been using ratios in math class for a few years now. Hopefully you've had some experience with them. I know we've done it earlier in the year. What is a ratio, though? A ratio is just simply any comparison of two numbers using division. We have three main ways that these look. The first way is that you could write it in words. You could say 3 to 4. So the relationship between 3 and 4, it's 3 to 4. You have 3 of these, you get 4 of those. You could also say it with a little colon. You could say 3 to 4 that way, using just the little colon to represent the word 2. Or, since technically this is a comparison by division, you could say 3/4 is the same thing. So 3 to 4 using the little colon, or 3/4. All say the exact same three. They're all examples of ratios, the exact same ratio, in fact. So let's do an example using these. So here we have a slightly more complicated ratio. We had 3/4 in the last one. Here I have a quadrilateral. It tells me that the ratio of the sides, there's 4 of them, of course, because it's a quadrilateral, are 2 to 3 to 5 to 7. So I've got 2 on one, I got 3 on the next one, I got 5 on the next one, and 7 on the last one. We know the perimeter of this quadrilateral is 85 feet, and that the length of the longest side is what we're looking for. So I'm going to go ahead and start off with a picture. Here's my quadrilateral. I know that mine looks like a rectangle, but I can tell from the side that it's not actually going to end up being a rectangle. It doesn't really matter that much. I'm going to go ahead and put the measurements on my sides here. I got 2 to 3 to 5 to 7. I'm going to use those as side lengths for now, just because that's all I have to go on. I know that can't be the side lengths, because when I add them up, it doesn't add up to 85 for the perimeter. So instead, what I'm going to do is I'm going to take that relationship and I'm going to try to maintain it. And I know that in order to get it to be the right size, I'm going to have to kind of blow that up, going to dilate that quadrilateral. And to dilate it, I'm just going to multiply all the sides to the same thing. I don't know what that thing is, though. I could guess and check, or I'm going to use my algebra skills. I know that it's the same number for all of them, so I'm going to multiply them all by that number, whatever it happens to be. Since I don't know it, I'm going to use x. So I'm going to go ahead and set up an equation. I know that 2 x's there on the left, and 3 x's on the top, and 5 x's on the right, and 7 x's on the bottom should add up to 85. I multiply all those by something. It should give me 85 as a total. Well, I can use my algebra. I can combine my like terms there. 2x, 3x, 5x, 7x. That's 17x total equals 85. And then divide by 17, I end up with 5. So if I take each one of these sides and multiply them out by 5, I get 10 and 15 and 25 and 35. And I add those together, I get 85 total. All right, so now I know what I'm multiplying them by. It's a matter of finding the length of the longest side, which obviously is the one with the 7. So I'm going to go ahead and plug in that 5 there. 7 times 5 is 35. Done. Used ratios on a quadrilateral. Let's move on. Next topic, proportions. Proportion is just simply anytime you take two ratios and you put them equal to each other. It says this ratio equals this ratio. Or what it almost always looks like in a math class is this fraction equals this fraction. So in my case, 3/4 equals 6/8, which I know is true because 6/8 reduces to 3/4. It's just doubling it. So it's anytime you have two fractions or two ratios, which are just a fancy term for fraction, equal to each other, then you end up with what's called a proportion. And we use these proportions all the time for finding extra bits and whatnot. Example of a proportion. Here we got 5 over y equals 45 over 63. Now, you guys may have experience with this. I certainly hope you've seen these before. We're solving for y. We don't know what it is. And we're going to use this trick they call cross multiplication, which is just simply I'm going to multiply by the diagonal of each other. So if you look, I'm going to multiply the y by the 45 and the 5 by the 63. I'm just kind of multiplying diagonally across, which gives me something that looks like this. I get 315, that's the 5 times the 63, and 45y, that's the y times 45. I'm going to go ahead and solve this. I'm going to divide both sides by 45. You get the y by itself, and I end up with 7 for the y. So I get y is 7. If I plug that in, 5 over 7 is the same thing as 45 over 63. Okay, moving on. How do we actually use these ratios and proportions in geometry in non-algebra ways? Because that was all just algebra review stuff. Let's add some geometry in there, some shapes. We're going to talk about similar figures. Similar figures are just simply figures that have the same shape, but are different sizes. So like our dilations that I mentioned before, when we did that earlier in the year, dilations are when you change the size of something, but you keep the shape the same. So here's the shape. I got a nice little right triangle there. I know it's 9, 12, and 15 as the 3 sides. A similar figure to that would be this little triangle here on the right. Each one of those sides is exactly 1/3 of what it started off with. It's all a little bit smaller. So those shapes, since they have the exact same right angle and same angles and whatnot, they're the same shape, but one's smaller than the other one. They just kind of shrunk it. So those are similar polygons. If I wanted to say that they're similar polygons, I'd have to give some points here. I'd have to put points. So let's say we got A, B, C, and on this one I'll do D, E, F. A, B, C, and D, E, F. And if I wanted to say that those are congruent, or not congruent, but similar actually, if I wanted to say those are similar figures, my statement would be that triangle ABC is similar to triangle DEF. And the way that I do that is just with a little tilde symbol between them. Triangle ABC, and then tilde, which represents the word similar, triangle DEF. So they're similar. That's technically called a similarity statement. So then let's use these. Let's go on. What do we do with their similar figures and proportions and ratios, and how do they all work together? Well, it's this thing called a similarity ratio, which is just simply how much bigger or smaller you're making something. It's kind of like that when we did dilations, we had a scale factor. It's the same thing as the scale factor. It's just written as a ratio, and it's got a slightly different term. It's a ratio of corresponding sides of similar figures. So you take the side from one figure, you take the side from the other figure, and you stick a fraction bar between them. You end up with a similarity ratio. So here's our same little triangles from the previous slide. I got 9, 12, 15 on one, and 3, 4, 5 on the other. I'm going to pick two sides. I'll happen to pick the 9 and the 3. And if I were to put them into a fraction, I would get 3 over 9. And that's my similarity ratio. I could do even better than that. I can go ahead and reduce it. 3 over 9, 1/3 is the technical final perfect answer for this. So my similarity ratio here is 1/3 because the little triangle is 1/3 the size of the big triangle. Generally, you put the smaller number on top. It's not 100% of the time. You don't absolutely have to under every circumstance, but it's considered the correct way to do it, to put the small one on the top. If you do it the other way around, people might kind of look at you funny if they happen to be a mathematician and take this kind of thing personally. But it's not necessarily wrong to do it the other way. Here's an example. Put it all together, one problem, final one. We have a boxcar on the left. We took this big boxcar. If you guys don't know what a boxcar is, it's one of those things that if you see the train going on the tracks, it's all the individual cars hauling whatever it is that they haul down those tracks all day long that we hear the train going by during class. Whatever's in those cars, it's called a boxcar. This one happens to be 9 feet tall and 36.25 feet long. I have a little model of a boxcar that my son plays with that's 1.25 inches tall, and I can't remember how long it is. So we're going to figure that out. We have 9 feet by 36.25. The model should be exactly the same proportions. So I'm going to set up a little proportion. I'm just going to match up the sides. I know that my 9 goes with my 1.25, and because it goes with the height, and my 36.25 is going to go with the x. Now you guys might be thinking, but Mr. Olivier, the one on the left, the boxcar is in feet, and the one on the right, the model is in inches. Don't I have to convert my feet into inches or my inches into feet in order for this to work? The answer is no. We don't absolutely have to, since everything on the boxcar itself is measured in feet, and everything on the model is measured in inches. All I really have to do is convert the 9 to 1.25 and the 36.25 into x. I can ignore the fact that it's different units because it really doesn't matter. It's all going to end up being the same in the end. I could pretend like it's 1.25 feet if it makes me feel better. But when I multiply everything out, it just cancels. It's feet over inches equals feet over inches, so it's the same deal. Let's go ahead and solve this. I'm going to use the same cross multiplication I used before. I know that 9 times x equals 1.25 times 36.25. Got some decimal action going there. 9 times x, that's easy. That's 9x. 1.25 times 36.25 is a little harder. I'm certainly not doing that in my head. 45.3125. Then I'm going to take that, divide both sides by 9. Once again, I'm going to pull out my equation, my calculator, sorry, and divide both sides by 9. I'm not doing that in my head. I get 5.03472 repeating. So if I wanted to kind of estimate it, I'd say it's about 5 inches long. So I can measure it. That seems about right. The little boxcar should be about 5 inches long. That's how much it is. Hope you guys enjoyed it. That's it for tonight. See you tomorrow.